Here is an image that is almost 2 megabytes big. And here is the same image, but now less than 90 kilobytes. That's over a 95% saving in file size. And to the untrained eye, there's little to no difference. In this video, I'll show you how to build your own image compression and optimization algorithm from scratch. But why is this important? Well, if you have a website, large images will completely kill your performance and also affect things like search engine optimization as well. And if you're like me from a data or machine learning background, large images can cause massive problems in training things like machine learning models. And in reality, having massive images doesn't always mean better quality data. Sometimes you can extract the same insight from a much more lightweight version of an image. So large images are great if you're taking pictures with your friends, but when it comes to optimization of systems, compression is really important. So let's dive into it. So for this build, we're going to be using Python and one simple package, which is the Pillow package, which is a pretty comprehensive package for anything to do with image processing in Python. Now, the first thing that we need to do is we're going to set up some classes. And the first class that we're going to create is a compression class. So by copying this code block here and inserting it into the compression folder, let's have a little look at what's going on here. So essentially at the start, all of the code that I've copied over so far are essentially just helper functions that the main method that's going to be used is going to make use of. So this includes things such as getting the shape of an image, loading an image from a bytes array, and also getting the actual size in bytes of an image as well. On top of that, there's some more helper methods as well, including the ability to be able to save an image to a file destination on the computer. So as I said, these are really just going to be used by the main compress method, which we're now going to take a look at here. So copying this across once again, I'll come back to the compression file and I'll paste this in, and now let's dive into this a little bit more. So this compress method essentially is going to take the raw image that we have within our file system and it's going to make it smaller. It's going to make it smaller in terms of the actual dimensions of the image, and it's going to make it smaller in terms of the file size. So if we take a look at some of these parameters that you can pass to the compress method, we're obviously going to pass the image file itself. We're going to pass the original size of the image, the path of the image, the file name of the image, which will be used later on to then save the image again. And then there's a few variables that are going to be used by the actual resizing part of the compression. So we have new size ratio, quality, width, and height. This ratio is a number between 0 and 1, and it's essentially going to be used to calculate the new size of the image. So for example, if we use a value of 0.8, then the new size of the image will be 80% of the original size of the image. And we have a quality parameter as well, which will be used by the Pillow package to essentially save the image at different varying levels of quality. So whichever value you decide to choose for the quality parameter, this will quite significantly affect the size of the images. And then we also have width and height. Width and height I'm not using in this particular scenario, but you can use these to actually hard code a specific shape that you want the output image to be created into. So this first block here essentially is just resizing the image into its new size. Either it's going to resize the image based on the new size ratio, or it's going to resize it based on the hard-coded width and height fields that you've provided. This next code block here is taking the resized image and saving it at the new destination, along with some optimization parameters and the new quality that we want to save it at as well. So when we save this new image, we're taking the original image, we're squeezing it down, and then we're simply saving it to a new file. And finally, this last code block is essentially just cleaning up some of the existing images that we may have temporarily have stored, converting the new image into a bytes array, and then passing this in the return line. So the act of actually compressing an image is very simple. Essentially, we're just squeezing down the dimensions and we're reducing the quality if needed. But compression isn't the only thing that we need to do here. Because let's say that you have an image which is several gigabytes in size. You might not necessarily know the optimal parameters to pass in order to compress this image. And you might want to get that image down to a particular size in kilobytes or megabytes. So really what we need is an optimization routine, not only to compress the image, but to keep compressing the image until it meets a certain threshold. And this is what we're going to do next. So now we're going to create the optimizer class. So I'll copy this code block and I'll put it into the optimization file. And now let's dive into this a little bit more. So let's take a look at some of the parameters that we can pass into this class. So we have an increment, quality, threshold, and the actual compressor class itself. As we'll see a little bit later on, this optimization routine will essentially go through a loop of continuously compressing the image until a threshold is met. And so we use this increment field to basically keep reducing the size of the image very incrementally until we're happy and that threshold is indeed met. The reason why we choose a small value here is because if you choose too large of a value, you could degrade the quality of the image unnecessarily. So if we increment in small amounts, and we have a certain threshold that we want to achieve with the image, which is of course stored in the threshold value here. So in this case, the threshold value that we want to stop the optimization at is 99 kilobytes, which for an image on the internet is quite small. Then the optimization loop will keep running, incrementing at values of 0.01 each time until we reach a file size of 99 kilobytes or less. So if the increment is too high, what we might find is that we might actually go over the threshold, but we might go over it too much. So by keeping the increment small, it means that we keep our file sizes as close as possible to around 99 kilobytes. So let's take a look at some of the other code blocks here as well. This first piece here is essentially loading the image from a bytes array, which comes from the compressor class, and then we're saving this image as well. So these are using methods that we already saw within the compressor class. Then we're taking the shape of the original image that's loaded, and we're entering this while loop. So this while loop is really where the optimization happens. So you can see within the while loop, the ratio that we're going to be reducing the size of the image by will keep incrementing by 0.01 each time, or whatever value you set to be that increment. So we start off with an image at its original size, and we keep reducing it down by 1% each time. It will then check the image size of this new compressed image and check to see whether or not it's greater than the threshold that we set. If it is still greater than 99 kilobytes, then it will continue and it will compress the image again, this time with a smaller ratio. But if the threshold is met, then we simply exit the routine and we return the bytes array. Now the reason why this is really important and really useful is because when images are used around the internet, simply compressing it once is useful, but sometimes on websites and, in order to abide by certain SEO principles, you want images to be a certain size. So by setting the threshold to a particular number of kilobytes, you can guarantee that your images will be underneath that size and meet the parameters that you need to address. So this actually came from a real need that I was working on for a particular business that needed images 100 kilobytes or less, and nothing over that could occur. So that's the main bulk of the optimization code explained. So now all that's really needed is to create our main module. So we're going to copy this code block and we're going to paste it in here, and I'll just talk you through what's going on here. So pretty simple really. We've done all the heavy lifting in terms of the two classes that we've created. So we're simply loading an image file. In this example, we're loading an image file from a file that's stored locally on the file directory. So in this case, image.jpg, stored in the same repository where the code is stored. But in reality, I've actually deployed this very algorithm as a serverless function on AWS. So rather than reading from a local file, it actually receives a string of bytes, and then it converts that string into an image within the serverless function. Or you could do it with a base 64 encoded string as well. So once we've loaded the image, we simply instantiate the optimization class and we optimize the image, and then we simply write that file to a file within our file system. So before we run this, let's actually have a look at the image, which comes in the GitHub repository that we're going to be running this routine on. So I chose this image purposely because it includes quite a lot of detail and it's a large image. It's just under 2 megabytes in terms of size. And as we saw from the parameters that are set within the class, we're going to be reducing this image down to underneath 99 kilobytes. So let's start the module. So quite a lot has happened there, and let me explain a little bit about what just happened exactly. So the image was loaded, and you can see that it's around 1 million bytes, 1,700,000 bytes in size, which is just under 2 megabytes. And as you saw when the code was running, it was clearly iterating in terms of reducing the size of the image, but it wasn't meeting that threshold, hence why it kept iterating further and further. And if you have a look at some more of the output here, you can see that the original shape, this is the actual size of the array that the image was loaded as. So this is the number of pixels essentially that we have within the image. And going a little bit further down, you can see each time it tries, the ratio gets reduced by an increment of 1%. So we start with the original image, then we go to the image at 99% of it, then we go to the image at 98% of the original size, so on and so forth. So obviously there's a lot to get through here, so I'm not going to go through every single loop that it went through, but if we scroll all the way down to the bottom again, now we can see the important information. So the new shape is now much smaller. The new size is around 95 kilobytes, which is underneath the 99 kilobyte threshold, which is perfect. You can see that the image was actually reduced by around 95%, which is pretty incredible, especially considering that it literally happened within a few seconds. And these final pieces of information here, so the optimization was complete at a ratio of 0.39, meaning that the size of the compressed image is around 39% in terms of dimensions of the original image. So in terms of the actual file size, we're reducing the file size by 95%, but the actual dimensions of the image is just over a third of what the original image was. So to kind of illustrate this a little bit more, let me pull up the compressed image and show them side by side. So first of all, you can see some clear differences. Of course, it's not going to be as HD and as clear as the original image, and a lot of the detail is a little bit more blurry. You can also see that some of the colors are a little bit less vibrant. But considering the size of this original image, if this image was displayed on a web page and it was displayed in quite a small dimension, realistically the difference between these two images would be negligible, but the performance gains would be significantly increased. So you can see some visual differences here. You can see that the size is slightly different, but to illustrate this a little bit more, let me open up the image files side by side rather than in Visual Studio Code. So you can see the original image on the left and the compressed image on the right. You can visually see here the size difference. It is around a third of the size if you just look at them side by side. And so this really demonstrates end-to-end how you can build your own image compression and, most importantly, optimization algorithm for all different types of use cases, for web development, for machine learning training, or just to improve the quality and the performance of your website. You can access the full code and documentation on my GitHub repository or from the Gumroad page where you can download the full blueprint ready to go. All the links are provided in the description below. And if you enjoyed this video, please give it a like and subscribe.